How do you draw time?
That is, that's quite the question, isn't
No,
it?
I mean literally. We have maps for space, right? We have
Wow.
coordinates for height and width and depth. So if you want to show someone where a mountain is, you just pull up a topo map. But when you get into theoretical physics specifically, special relativity time isn't just a ticking clock in the background. It's a dimension. It stretches, it squashes, it twists.
Precisely. It becomes geometry. And that is where things usually get very difficult for the human brain to visualize.
And that's our mission for today's deep dive. We are looking at a stack of documents that are technically a changelog. It's a series of Python scripts for a piece of software called symmetric spacetime. But reading through them, it feels less like a manual and more like a diary of someone trying to visualize the invisible.
It really does. We're tracking a very specific burst of development here. It's a set of iterations for a Blender add-on, specifically Blender 4.3 and up. We're looking at versions 5.0 through 5.28.
All created by a developer listed as Xenon Gemini.
Yes. And the timeline is incredibly compressed. This all seems to happen around February 20th, 2026. It's rapid iteration. They were adding features almost as fast as users were asking for them.
It's basically a coding sprint.
A massive one. And the goal is audacious. They aren't just trying to make a pretty animation for you to look at. The source code explicitly calls this tool a proof of time balance.
That's a heavy phrase for a Python script, proof of time balance. It sounds like something you'd find carved on a stone tablet, not sitting in a GitHub repository.
It is heavy. But as we dig into the math inside these scripts, you'll see why. They are trying to prove that no matter how you distort space with speed, the time account of the universe always balances out.
So we are going to trace this journey today. We'll go from a clunky, kind of rigid simulation in the early versions to this fully customizable, glowing multi-ray physics engine in version 5.28. But before we get to the pretty lights, we have to eat our vegetables. We have to understand the math foundation.
Fair enough. You really can't appreciate the solution if you don't understand the problem.
Right. So in the earliest version, we have version 5.2 ARA. The physical setup is described as having two arms, arm A and arm B. For the non-physicists listening to us right now, are we talking about robot arms?
Think of them more like the arms of an interferometer. Imagine a capital letter L. You have a corner point, which is the center. One arm shoots a laser beam to the right, that's arm A, and the other shoots a laser beam upwards, that's arm B.
Okay, standard physics experiment setup, Michelson-Morley style.
Exactly. And the script defines a few key variables that control this little universe. You have radius, which is essentially just how long the arms are, and then the big one, velocity.
This is the V over C I saw scatter all over the code.
Exactly. Velocity divided by the speed of light. If you set the slider to 0, you're standing still. If you set it to 0.9, you are moving at 90% the speed of light. And this is where the engine kicks in. The code calculates something called gamma.
I saw gamma mentioned a dozen times in the comments. We need a quick definition here. What is gamma?
Gamma is the stretch factor. It's the mathematical consequence of moving fast. If you move at high velocity, space contracts in the direction of motion, and time slows down for you. Gamma is just the numerical value that tells you exactly how much.
So if the code calculates a gamma of, say, 2.0, then time is running half as fast.
Essentially, yes. And in the 3D visualization, that means the path the light takes has to get geometrically longer to compensate.
Okay, so we have this L shape. Light goes out, bounces off a rigid mirror, comes back. Simple enough. But in version 5.20, there was a problem. The developer notes say arm B was locked.
It was completely rigid. Arm A was always on the x-axis, and arm B was always on the y-axis, a perfect 90-degree angle. Now, that's fine for a simple textbook diagram, but the universe isn't always perfectly perpendicular. If you want to prove that relativity works everywhere, you can't just show it working in one specific corner case.
Which brings us to version 5.21. The developer introduces a new property, a variable called arm B angle.
This is the first big leap for the tool. Suddenly, that second arm isn't stuck at 90 degrees relative to the first one. You can adjust it.
Anywhere from 0 to 360 degrees, right?
Right. 45 degrees, 120 degrees, 17 degrees. You can spin that second light beam anywhere in the circle.
And this is where that proof of time balance concept actually clicked for me. Because I was looking at the output logs, and something really weird happens when you change that angle.
What'd you notice?
Well, physically on the screen, the shape changes entirely. The light path gets longer or shorter depending on how it's angled relative to the velocity. If I point the arm in the direction I'm moving, the light has to chase the mirror, so the path is huge. If I point it backwards, the mirror rushes to meet the light, so the path is incredibly short.
Correct. The geometry becomes wildly asymmetric.
But the time accounting box, there's this value labeled A, it never changes. It's rock solid no matter what I do to the sliders.
That is the magic trick of the whole script.
Explain that. How can the visual path change length so drastically, but the total time it takes remains perfectly constant?
Because the simulation is actively compensating for the movement of the frame itself, the code is calculating the out time, which is the light leaving, and the in time, which is the light returning. Depending on the angle, maybe it takes a very long time to go out, but a very short time to come back, or vice versa. But when you add out plus in, it always sums up to that constant value A.
So the code is basically asserting that the speed of light is constant relative to the observer, no matter which way you point the laser.
Exactly. It's a literal digital proof of isotropy. The universe doesn't care which direction you look. The rules of time apply equally. The math forces the books to balance.
That's comforting in a way. Even at light speed, the accounting department is still doing its job. But I want to pivot to something that feels a little less like physics and more like hacker magic.
You're looking at the dynamic defaults section.
I am. There's a block of code labeled current defaults. Now, usually when you use a piece of software, let's say you're using Photoshop, if you change your brush size and then you close the program, you lose that setting unless you specifically saved a workspace file somewhere on your hard drive.
Right. Most programs keep the application code and the user settings completely separate. It's safer that way.
But this script does something I really haven't seen before. It seems to rewrite itself.
It does. It's genuinely fascinating. There's an operator built into the UI called WMOT, copy full script.
Catchy name. Rolls right off the tongue.
It does exactly what it says on the tin. Let's say you're the user. You've set the velocity to 0.5. You've set arm B to 30 degrees. You like this setup and you want to keep it. You press this button.
And what actually happens under the hood when you press it?
The Python script reads its own source code, literally the text file that is currently running in Blender's memory. It scans through the text until it finds the dictionary called current defaults. It erases the old values. It physically types in your new values, the 0.5, the 30 degrees. Then it copies that entire newly modified block of code to your computer's clipboard.
So you just paste it back into the text editor and you've effectively genetically modified the program to remember your preferences for the next time you run it.
Precisely.
Yeah.
It's a clever self-saving mechanism that doesn't rely on external configuration files. It carries its own state within its own body. It adapts to you.
I love that. It's like the code is evolving based on how you interact with it. But evolution isn't always a straight line, is it?
Oh no. Software development is messy.
We have to talk about version 5.22. The Oops update.
The developer got a little too aggressive with the pruning shears there.
The notes say they were trying to simplify the UI to make it cleaner, and they accidentally deleted the links panel, which tells you how to access the Notion documentation to use the thing, and the system panel, which allows you to cleanly remove the add-on.
Imagine building a high-performance car and deciding the door handles disrupt the aerodynamic flow, so you just weld the doors shut. Great for speed, terrible for getting in and out.
We have achieved perfect aerodynamics, but now I am trapped inside the car.
Exactly. But to their credit, they caught it immediately. Version 5.22 brings those panels back. However, the real drama, and I think this is the most relatable part for anyone who has ever done 3D design work, was the color crisis of versions 5.23 and 5.24.
The color crisis. Sounds like a bad political thriller.
It was a very real battle against the software cache.
So walk me through this. The user wants to change the color of the light rays, maybe make arm A red and arm B blue. They drag the color sliders in the menu, but the source material says nothing happens in the 3D view. Why?
It comes down to how Blender handles memory. Blender is a very efficient program. It doesn't want to create new materials if it doesn't absolutely have to.
It's lazy.
It's frugal. If you have a material named ray material and you tell the script to make a new ray material that's red, Blender looks at its internal list and says, well, I already have something called ray material, just use that one. And that one happens to be the old blue one.
So the user is screaming at the screen changing settings, but the visual is locked.
Exactly. And for a scientific visualization tool, that is a death sentence. If the visual doesn't match the data, the tool is actively lying to you.
So how did they solve it? The changelog for version 5.24 mentions unique material logic.
They stopped using generic names entirely. Instead of calling a material ray A, the script now generates a name that includes the exact data. So the name becomes something like Matt Arm A, out 1.00, 0.50, 0.0000, and so on.
Wait, so it puts the actual RGBA color values directly into the file name?
Yes. So if you change the color by even 1%, the name fundamentally changes. Blender looks at it, sees a string of numbers it's never seen before, and is forced to generate a brand new, unique material.
Brute force. I like it, but doesn't that create a huge mess? If I drag a slider back and forth for 10 seconds, aren't I creating thousands of junk materials in the background?
You absolutely would be, which is why they had to add a cleanup duty function called purge unused materials. Every time the script updates, it acts like a garbage collector sweeping away the materials you aren't actively using anymore. It keeps the Blender file from getting totally clogged.
It's interesting how much invisible plumbing is required just to draw a simple line correctly on a screen. You think it's just math, but it's mostly memory management.
That is the reality of software development. Yep. 10% is the elegant math. 90% is making sure the colors update and the buttons actually work.
Speaking of the colors updating, there was another visual upgrade in V5.24 that caught my eye. They messed with the principled BSDF nodes.
That's the standard realistic material shader used in Blender.
They added emission strength. They cranked it up to 3.0 initially, then dialed it back to 2.0 in later versions. Why does that specific setting matter?
Because up until that point, the rays were just colored tubes. They look like plastic pipes floating in a void. By adding emission, they interact with the renderer as actual light sources.
They glow.
They bloom. Against a dark viewport background, they look like real lasers. And that is important for the user's intuition. You need to feel like you're working with raw energy, not plumbing fixtures.
So by version 5.26, we finally have a robust working tool. It saves its own settings, the colors update correctly, the rays are glowing, and then the developer decides to just throw the kitchen sink at it.
Yes. Restoring the visual aids.
Yeah, suddenly we get tube rings and ellipses and skeletons. What exactly are we looking at here?
Context. If you just have two floating laser beams in a black void, it is incredibly hard to perceive the curvature of space. You need structural reference points.
So the ellipse is what? The path.
The ellipse represents the event locus. It's the collection of all possible reflection points. Imagine if you fired light in literally every direction at once. The outer boundary it forms would be this relativistic ellipse.
And the tube rings?
Those are static parallel circles. They act like a rigid mirror structure. A ruler or a grid showing you where normal space is so you can clearly see how much the moving light is deviating from it.
And the skeleton.
Vertical lines connecting the start and end points of the paths. Think of it like the wooden studs inside a wall. They show you the rigid, non-relativistic structure of the device, while the glowing light rays show you the flexible warped path of the actual energy.
And the notes really emphasize that the user has granular control over all this. Every single element, the rings, the skeleton, the ellipse, has its own independent line thickness and color control.
That granularity is key. If you were a teacher trying to explain a complex physics concept to a student, you might want the skeleton to be very faint, just a gray ghost in the background so the bright red laser beam pops. Or maybe you want to focus entirely on the geometric bounds so you make the skeleton thick and the rays thin. It puts the hierarchy of visual information completely in the user's hands.
Which brings us to the final boss of this deep dive, versions 5.27 and 5.28, the massive leap from 2 rays to 12 rays.
This is where the tool officially stops being a simple diagram and becomes a full-blown complex simulation engine.
Up until now, we've been visualizing a simple V shape or an L shape. What happens to the screen when you toggle 12 rays mode?
Imagine a clock face. Instead of one beam of light, you have 12 distinct beams, all firing simultaneously from the center, spaced evenly apart like the hours on a clock.
That sounds chaotic.
It can be, but it allows you to see the actual shape of the time dilation. It's not just a single line stretching anymore. It's an entire expanding bubble of light being actively distorted by velocity.
And in the final version, 5.28, they introduced 2 distinct geometric patterns for this, pattern A and pattern B. Now, pattern A is the classic explosion. Light travels from the central start point out to the ellipse and back to the center. But pattern B sounds trippy. The notes call it converging.
This is the pattern that really tests the limits of the math engine. In pattern B, the light starts at the circumference, the bottom ring. It travels inward, converging to the center, hits a mirror, and then travels up and outward to the top circumference.
So it's like an implosion.
It's like a reverse firework. And for the underlying code, this is a massive headache. You are no longer calculating from a static 0, coordinate. You are calculating from a moving point on a spinning ring.
The code mentions specific functions for this. There's get p rigid versus get p final. I assume p stands for point.
Correct. P rigid is where the mirror physically is right now. P final is where the light actually hits it after you account for the time it took the light to get there. Because remember, while the light is traveling inward, The center mirror is actively moving away from it down the track.
It's like trying to throw a baseball at a target that is actively running away from you.
Exactly. And the Python code has to solve that intersection perfectly for 12 different rays simultaneously across 3 dimensions.
With 12 rays going in and 12 rays going out, plus the skeleton lines, plus the tube rings, plus the ellipse, I'm imagining the Blender viewport is just a spaghetti mess of geometry at this point.
It absolutely would be. If you just turned every single element on at once, it would be completely unintelligible. And that brings us to the transparency debate found in the developer notes.
Yeah, I saw this back and forth in the logs. In version 5.27, they tried implementing a global alpha slider.
Right. One transparency slider to rule them all. You drag it down and everything on the screen uniformly becomes 50% transparent.
But that didn't stick around.
No, because it's a blunt instrument. If I make the messy structural skeleton transparent, I also accidentally make the important glowing light rays transparent. I lose the signal along with the noise.
So in the final version 5.28, they reverted to individual alpha sliders for every single component.
Yes, it is technically more work for the user.
Oh.
You have to tweak 5 sliders instead of just 1, but it allows for actual depth. You can make the background rings 10% visible, so they are barely there, and keep the main light rays at 100% solid opacity. You are essentially compositing the image in real time to clarify complex 3D intersections.
And to help with that user experience, they also added the eye icons.
A classic and essential UI element.
These toggle Boolean properties like show ray out or show ray in, they sit right there in the sidebar.
This is absolutely crucial for the converging pattern we just talked about.
Yeah.
If you show the inbound implosion and the outbound explosion at the exact same time, it's just a dense web. You can't tell what is actually happening.
So the user can just click the eye icon, hide the inbound phase completely, and just focus on the outbound result.
Right. It allows you to dissect the physical event, hide phase 1 click, show phase 2 click. It turns a monolithic physics model into a dissectable interactive object.
But here's the detail from the source material that I found most profound. The notes mention time accounting persistence. Even if I click that eye icon, even if I hide every single ray, and the screen is physically empty to my eyes, what happens to the math?
It keeps running in the background.
The text box with the value A, the total time accounting it, stays on the screen and keeps calculating.
It does. It never stops.
I find that weirdly philosophical. The physics engine is perfectly calculating the relativistic path length of a light ray that I have technically deleted from my vision.
Well, that is the entire point, isn't it? The universe doesn't stop working just because you close your eyes. The code is running the simulation of the physical constants, whether you choose to render the geometry in the viewport or not. The mathematical truth exists independent of the visual observation.
The truth exists independent of the observation. That is quite a bold claim for a Blender add-on.
Maybe. But if you think about what this tool actually represents, we have gone from version 5.20 to 5.28. We've gone from a broken, rigid L shape to a glowing, self-correcting, multi-dimensional simulation engine. And through all those chaotic changes, the material renaming the color crashes, the transparency fights. The one thing that never ever changed was that constant value A.
Time balance.
The time balance. The developer spent all this incredible effort changing the presentation, the colors, the angles, the UI panels, but the underlying truth, the math of special relativity, remained rock solid the entire time.
It almost feels like the Python code is just a visual wrapper desperately trying to catch up to the perfection of the physics.
That is a very accurate way to put it.
So here's the final provocative thought I want to leave you with today. We usually think of computer simulations as mere approximations. We say, oh, it's just a model. But this specific script forces the geometry to obey the math of relativity so perfectly that the time accounts always balance out to the decimal.
Where are you going with this?
If a simple Python script written in a compressed timeline by one developer creates a digital universe that perfectly adheres to time dilation no matter how you warp it, does that make it just a model? Or does that act as a digital proof? Is the grand symmetry of our actual physical universe really just a few lines of elegant code waiting to be properly visualized?
That is definitely something to think about the next time you are staring at a loading screen progress bar.
Indeed. Thank you for joining us on this deep dive into the geometry of space-time and the iterative code that tries to capture it. Take a moment to think about the geometry of your own timeline. Check your local frame of reference, and we will catch you on the next one.